Hi students, welcome back, and today I will be putting up a video on how to solve the derivation from the chapter Oscillations in your 11th standard textbook. So this derivation is about finding the time period of a simple pendulum when it is displaced by a small angle theta. Okay, so the first step before we start solving is to draw the diagram, and we know how to draw a pendulum diagram. This is the rigid support by which it is going to be held. Our pendulum will be of length L and the bob will be of mass M. Now this is at a mean position where x is equal to 0. We need to displace it by an angle theta. Okay, and this angle theta is very small. This is the assumption that we have to remember. Now when this bob reaches this maximum displacement, okay, the small displacement that we have done, we need to identify the forces acting on this bob. So how many forces would there be? Correct, some of you have thought it. First force that is going to act on it will be mg, that is your gravitational force, and the second force that's going to act on it will be your tension force. Okay, now based on these two forces, only these two forces are acting on it. There is also something else that is acting on it, and that is a restoring torque. Now we know that we have displaced our pendulum bob, okay, in this direction, then the restoring force will be in the opposite direction. This is nothing but it is also the restoring torque. We say there is a torque created, but it is a restoring torque because it is restoring the bob back to its main position or towards its main position. Okay, so now let us resolve the vectors into its components. So we are going to resolve mg. So if I resolve mg, I will get at this theta angle, I will get mg cos theta, and here I will get an mg sin theta. Yes. Okay, once you've done this, then you can go on to write a little bit about the derivation. Okay, this is important. You have to write something. Okay, so you need to write, consider a simple pendulum which is having a small bob of mass m tied to an inextensible massless string of length L. The other end of the string is fixed to a rigid support. The bob oscillates in a plane. Okay, and let theta be the angle made by the string with the vertical. When the bob is at the mean position, what would be the value of theta? Yes, it's going to be 0. Okay, there are only two forces acting on the bob, the tension T along the string and the vertical force due to gravity, which is mg. You can further write that mg can be resolved into two components, mg cos theta, mg sin theta. Now what is happening if you see closely, the torque over here, okay, the torque here and mg are in the opposite direction, and since they are in the opposite direction, they will cancel out each other. So what remains finally is nothing but mg sin theta. Okay, and now what is this mg sin theta? It is nothing but it will be the torque that is restoring the bob back, so it will be called the restoring torque. Okay, the force that is making sure that the bob is coming back, okay, is going to be your mg sin theta. Now since it is restoring back, we will put a negative sign which represents that it is moving in the opposite direction. Okay, the force that is pulling it in the opposite direction. So now we know the formula for torque. Torque is force into the length. Okay, so when I do force into length, I can write force as minus mg sin theta into capital L. This can be further written as mg L sine theta. I'm only writing it like this so that I have a better or clear looking picture of the equation, okay, where sine theta with its angle is on the end, towards the end rather. So this is equation 1. Once you get this equation, you have to understand that now we have to look at how the torque is being applied, because it is also a rotational motion, okay, that's playing its cards here. So in that essence, we know that torque is I alpha, where what is I? I is going to be our moment of inertia, and what is going to be alpha? It is angular acceleration. So we already know this. Okay, now I am going to only do one thing. I'm going to keep alpha on one side and take the terms on the other side. So I will get tau upon I. I know what is tau. I know what is the torque. It's minus mg L sine theta upon I. This is it. This is what I have to get. Now, in the very start I had said that the angle by which we have displaced it is very, very small. That means theta is small. And if theta is small, what do we consider? We say that sine theta is approximately going to be theta. This is the assumption that we make. And because of that, what will happen to the above equation? We will get, yes, try solving this part. Yes, we will get minus mg L theta upon I. Okay, so this is going to be our equation 2. Right? Once we have all of this in place, now we have to also realize that there is another equation that we can make use of over here, and that equation is alpha is equal to minus omega square theta. Okay, alpha is equal to minus omega square theta. This is the angular acceleration in SHM. And when I look at this angular acceleration in SHM, it is an analog. Okay, we are going to compare this equation 3 with equation 2. So on comparing equation 3 and equation 2, on comparing equation 3 and 2, we get, what do we get? We are only looking at omega square now. Omega square is equal to mg L upon I. This is it. Okay. So once you get omega square is equal to mg capital L upon I, now we have to substitute certain values. L will remain as it is, G as it is, M as it is. All we can do is work on our I. What is I? Moment of inertia. Do we know how to find moment of inertia? Yes, moment of inertia is mr square. But here, okay, we are not looking at a radius. Rather, the radius here is our length. So, it is ml square. That's it. So, substituting r is equal to ml square in this equation, what will we get? We will get mg L upon I. I is ml square. So cancel L, 1L, my 1m, my 1m. That's it. Once I reach this, okay, what will be my answer? G upon L. Now, do I need omega square? No, I need omega. So I'm going to take the square that side. It will become root of G by L. But what is omega? Because we are still, what is our goal? Our goal is to find out time period. Okay, can I use omega to find out what is the time period? Yes, because I know that omega is 2 pi upon capital T, which is the time period. So now I will just put this equation here, 2 pi by T. Therefore, you can say 2 pi by T is equal to root of G by L. Now take the T on top. 2 pi will remain as it is. Root will become L by G. And this is your final equation. Okay. This is it. This, my dear students, is what you have to achieve. Okay. This is the time period of a pendulum. And if you have done your practicals, then you know this is the same formula you use in your lab. That is it. Okay, so you have to only remember the key steps. The key steps are right here. I'm just going to show you. You have to first draw the diagram. Make sure all the forces and everything is shown. You write a small write-up about what this diagram is and how you're going to start the derivation, what you're considering, okay, the assumptions you're making, and then you start. First you start with the torque formula. You come to this equation 1. Then you write torque in terms of angular acceleration and moment of inertia. Then you substitute the value and find what is angular acceleration. And when you get angular acceleration in equation 2 here, you are going to compare it with its analog. Okay, that is alpha is equal to minus omega square theta. On comparing 2 and 3, you will get what is omega square. Omega square is only this section of equation 2. So that is mg L upon I. Now, some students may also solve it differently. Okay, from here I can also solve it by putting this under the root sign. Okay, pay attention. I can write this like this, and I can directly write this as 2 pi by T and then solve it further. Okay, or I can directly substitute value of I and first only cancel the components. That's it. So once you substitute the values, you substitute what is omega, which is 2 pi by T. You have arrived at your equation, the time period of a pendulum. I hope you've understood this. It's a simple derivation. If you understand the flow of it, you will be able to solve it very easily. So thank you, students. Learn and keep revising. Bye.